The last is hypothesis testing using p-values, which is slightly different flavor of the z scores. So looking at the diagram of my normal curve, I'm noticing that if I have two values of z, minus z1 and z1 over here, the areas outside of the areas in the critical region, so outside of z1 and below minus z1, uh, if if the value lands within any of those critical regions, it's essentially more extreme than any of the allowed values. So at least as extreme as the one obtained by the test statistics or more extreme. So in this case, if the test value is within any of those regions, we can essentially say that the null hypothesis can be rejected. And the way to get the p-value is from calculating the test score and then comparing the value of the test score with the tables to get the probability value, and finally constructing the p-value by multiplying the probability value by 2. We'll see exactly what this means by example. And the p-value is twice times the probability that any given test score is going to be greater than the absolute value of z1. So I'm talking about this specific area here. So this is the area that the half of the p-value is, same as this area over here. And p-value is twice the size of that area. And we can get the size of this area from our tables. So the rule is if the p-value is greater than 0.05, we fail to reject the null hypothesis. If the p-value is less than 0.05, we reject the null hypothesis. Cool. So how does it look on example? Well, the Department of Education believes that a score obtained in a certain test is normally distributed with a mean of 70 and a standard deviation of 6. A random sample of 36 students take the test and their mean score is 68.5. Using the p-value, carry out the hypothesis test to check if the claim about the mean of the population is true. So what are we going to do? Well, first of all, we're going to state my null hypothesis, H0. We're going to state that the mean is equal to 70. So then the alternative hypothesis H1 will be simply that mean does not equal to 70. Okay. So then we're going to state that 5% level of significance leads to p-value of 0.05, also written as alpha equals to 0.05, the size of the critical region, let's say. So first is the next step is to find the z statistic. Z equals to again x bar minus mu divided by sigma over root n. So in this case, n equals to 36, x bar equals to 68.5, and we already know the values for the mu and for the sigma. So that means that z equals to 68.5 minus 70 divided by 6 divided by root 36, and that is a value of minus 1.5. So this is the z value. So if we're looking at z value equal to minus 1.5, so the p-value is given by twice probability that z is greater than absolute value of minus 1.5, which is twice by 0.0668668. The way I find this value is I'm rewriting this as probability of z being less than 1.5 and taking that probability from minus 1, and finishing that calculation, I'm going to get that p-value is equal to 0.1336. Okay, so that's my p-value. That leads me to a conclusion that because p-value of 0.1336 is greater than 0.05, we do not reject H0. So you can notice that we could have done this problem using the first method, simply because the z-score is greater than minus 1.96 and less than plus 1.96, but the problem stated that we have to use the p-value to carry out the hypothesis test. Okay, that's the end of the example set. I hope this made sense, and please let me know if you have any questions.